this master-slave topology, whereby you have one master server, as you've had thus far, but then you also hang off of it one or more slave databases, as they're called. And their purpose in life is to read data that's being written to the master so that they always have copies of the master. Now, what's the advantage here? In this topology, we have 3 slaves, 1 master. What's the value add, then, of introducing servers 2, 3, and 4 here? Because they seem to have some fundamentally distinct roles, at least semantically. That would seem to be the case if one's being singled out as master and everything else as slave. Yeah?
The read queries can get divided over 4 servers, or the write queries have to go to a single master.
OK, good. So if we leverage that assumption we made earlier, which was that reads are more common than writes, and this is quite often the case, not always, but in the case of Facebook and probably most websites that you've worked on for this class or others, they're probably a little more read-heavy than they are write-heavy. Certainly as they get popular, you get more readers than writers, perhaps. So if that's the case, you could just write your code in such a way that anytime you do an insert or a delete, or more generically, a modification to your database, you send those queries to the master. Whereas if you just want to do a select and some joins, you would do those on any one of the slave databases. So in this sense, you can optimize one server for writes, and then you can triple the amount of capacity you have for reads. So this sounds great, but what are some of the downsides or costs here? Yeah?
Can the slaves be read as they're written to?
Can the slaves be read as they are written to? Good question. Hopefully the database provides us with some form of integrity so that if we do a select while a query is being replicated from master to slave, that we're not going to get part of a row. And indeed, that's one of the things that a transaction-safe database would do, in that you're either going to read the whole row or none of it if you use something like locks or transactions. So in short, we can solve that. Other problems or costs that arise once we introduce slaves 2, 3, and 4 here?
You run into problems of sort of reading before a write has been passed.
Exactly. So what about consistency here, right? Even though you are replicating the data from master to slaves, that's got to take some amount of time, even if it's just milliseconds or microseconds. But in that window of time, suppose that the user has a second browser open, or suppose another user tries to pull up your profile roughly at the same instant you're actually updating it. That begs the question, what are those 2 users going to see? In fact, this too, you can occasionally see symptoms of this on Facebook, whereby you might update something and then it doesn't actually appear. And maybe when you reload, it's there, but it doesn't necessarily propagate instantly to that same browser window or another browser window. And that might not be a bug per se. That might simply be propagation delays. And in fact, even though in the ideal world this happens nearly instantly, it can still take several milliseconds, even a few seconds, if all of a sudden you get hammered with a huge number of writes. That might take some time for that buffer to clear and actually propagate to the slaves. There's actually a really interesting Facebook blog post from a couple years ago that I'll try to dig up and post on the lectures page, where they discuss the rollout of their East Coast data center. I believe they started with one main West Coast data center. And then for latency and scalability purposes, they, a few years back, added an East Coast data center. And the idea was to, one, be able to handle more users, but also decrease the number of milliseconds it took for East Coast folks to actually pull up Facebook content. If you have a server on the East Coast and you're on the East Coast, you can assume 10, 20, maybe 30 milliseconds of latency for the round-trip request and response to come back, which is pretty fast. If you're going cross-country, though, it can rise to 70 milliseconds, 100 milliseconds. So you could have that by having an East Coast presence, and never mind the implications for Europe and Asia and the like. So when they did this, though, there was an issue, because it was relatively easy, according to their blog post, to just do some replication of slave databases, or the equivalent, on the East Coast, so that you could have much more proximal and quicker reads, so you could access data more quickly. But writes, for technical reasons, were still pushed to the West Coast, as I recall. And I might be flipping the story, but I think this is the direction that things were going in. They still had all of their masters effectively on the West Coast, just because it was going to be hard to put masters at the time on both sides, or it was going to require at least more work. So the problem here, though, is that if I'm in harvard.edu and I update my Facebook profile, that update needs to get propagated to the West Coast. But then for performance, they wanted my reads and my reloading of the page and subsequent link clickings to come off of servers on the East Coast. So there was this delay potentially that you would see if things got backed up in the transfer process from West Coast to East Coast. And the article actually talks about some really interesting solutions they came up with, whereby I think one of their solutions was when you do make an update to a page, say your profile page, they would plant a cookie in your browser that would say, hey, I updated something recently. And that cookie would have a lifetime of a few seconds or a few minutes. And that cookie would be used by their own load balancers to decide to keep sending you to the West Coast, at least for a few seconds, so that you see the very latest information, even though it's taking a few more milliseconds to get that round trip there and back. And then once that cookie expires and they assume that the replication has happened, then you get rerouted back to the East Coast. But there are these hoops you have to jump through. And Facebook is certainly not representative of most websites out there, but the number of technological problems that they actually face is really quite fascinating. And I will say, every year they bring out faculty and TAs to Palo Alto to talk about and see some of the technological problems they're working on. And if you do have an interest in scalability, whether it's hardware or software or networking, like Facebook and Twitter and a couple of their counterparts really work on some fascinating scalability problems that are really unprecedented until recent years. So what else is problematic about this besides potential propagation delays? What else can go wrong here? Or what's still wrong here? Yeah.
Will the writes still go to single master? So if that gets too full.
Yeah, so we've kind of just avoided the problem or postponed the problem a little longer. But if our traffic continues to rise, we still have, one, a bottleneck in the form of the master. And we also have a single point of failure, which means if he goes down, we can continue reading, but no one can update their Facebook profiles at all until we get that server back up. Now, one of the compelling features of master-slave relationships is that you can relatively easily promote a slave to master in the event that the master dies. And you could do that automatically with some scripts, or a human could intervene and actually tweak a configuration file. But at least it's a compelling feature, whereby if, in the worst case, your master dies and your super fancy write server goes offline, at least within a few seconds or minutes you can promote one of the slaves, because it should be a perfect copy thereof. But what else could we do here? Well, this is called master-master replication. And based only on the picture, what problems does this solve? And what problems remain?
You can have multiple masters, so you no longer have the problem of the one master getting too full.
OK, good. So you have multiple masters, so you no longer have the obvious problem of just one master being full. You no longer have a single point of failure. You have 2 points of failure, but at least probabilistically, that they're both going to die, you would hope, at the same time, is at least a little less likely than just one of them dying. So that seems a plus. But what problems remain? So there's still some latency. So the arrows from left to right and right to left suggest that in addition to replication from master to slave, master-master replication is also happening here. So in this kind of model, you might very well have another device in the picture, like a load balancer, that decides either via round robin or via load to send inserts and deletes and updates to this guy or to this guy, or maybe always to this guy, but the other guy is always getting copies of them so that he can be promoted if one of them dies. But in short, you introduce some more robustness here, more reliability, but there's also a cost, quite literally financial, right? So it's very easy to just say, well, if we have single points of failure, let's solve the problem by doubling the amount of hardware we have. But this literally has non-trivial implications. As an aside, and as you kind of think about what you might want to do longer term if running your own site, Amazon also has an elastic database service whereby you can create a MySQL topology and have it scale laterally with replication even just by running some commands or clicking some buttons on their website. So you don't need, even though we've drawn things here as pictures, as from this book excerpt, you don't need actual physical hardware. So now let's paint a more complex picture, which is perhaps a little more representative. So at the top, we have some client network like the internet. We have the load balancer. We have a whole bunch, 5 of web servers. The arrows then are pointing downward. Let me zoom in if the text is a little small. The arrows are then pointing apparently to a load balancer on the left that then dispatches across MySQL slaves. And then we have one master server on the right that is replicating in turn to the slaves down below. So it's getting complicated, frankly. So it's getting expensive. But we're starting to now combine some of these ideas. But there's still some excuse me, there's still some problems here. Find fault with this topology. Yeah, Zach.
Still all the requests are coming to one load balancer.
Yeah.
One point of failure at the top.
Right? It doesn't matter how like fancy your internal architecture is, how pretty your network topology picture is, no matter how impressed your boss is, like you're still an idiot if you still have, despite all of this effort, a single point of failure that could have been avoided. Now, in fairness, maybe it's a financial decision, and maybe what you do in this case, because this is all you can pull off financially, is maybe you invest in a very expensive load balancer for the very top of the picture, or at least a very expensive support contract, so that if it does go down, the company will replace it within 4 hours, literally on site. So this kind of mitigation is possible. But if you're just doing it and then crossing your fingers, not the best idea. So what would be an obvious refinement here? OK, yeah. I mean, sometimes it's as simple as that, like multiple load balancers. And indeed, what you can do then is have 2 load balancers that dispatch across those 5 servers. But now we're adding a complication. If we've got 2 load balancers, what's the implication for DNS and for the IP address and all of this? Like, how do I decide which load balancer to send traffic to? RJ?
You could add a load balancer to the load balancer.
You could have a load balancer to the load balancer, and this seems to be kind of a vicious cycle, right? Because then we have a new single point of failure, so we need a second load balancer, but now we have to balance load across these 2. So hopefully there's a solution here. And indeed there is. So there's network level tricks that you can do whereby we could introduce to this picture 2 load balancers side by side, but that have only one IP address. And what you do is configure the 2 servers in such a way that they are highly available. HA is the buzzword here. And what they do is they send heartbeats to one another, which is essentially like a ping from left to right and right to left. And what happens is as soon as one of those servers does not hear the heartbeat from the other, it assumes that he is down, and what the remaining server does is take control of that IP address at a network level. And this is done if you're familiar, if you took 143, ARP is involved here, ARP, Address Resolution Protocol. The server gets involved and then says, I shall be henceforth IP 1.2.3.4 until this guy is brought back online, and then maybe you can have the IP address back. So you have one IP, but it floats across 2 servers, and they decide dynamically whether or not the other guy is alive. Now, of course, problems here could happen too. Find fault with this story. What else could die in this story, even if it's not pictured on the image?
The network between the 2?
Perfect, right? What are these 2 load balancers connected to? Well, probably a switch, like something bigger and more expensive than the switch or the home router you have at home, but 2 Ethernet ports. Now, if those 2 Ethernet ports are in the same device, you're still an idiot, right? Because you've just now moved the single point of failure from server level to network layer, but this too is bad. So typically in this picture, we would scroll up even higher, and we would actually have 2 switches in the picture. And you would actually connect this load balancer to this switch, and to this switch with 2 Ethernet cables, and then this guy would be connected conversely to both of them across both switches. So you really have this mesh effect. And even though this is getting increasingly complicated, these are actually robust engineering solutions to this. But this is why, frankly, services like Amazon's are so increasingly compelling, because my God, like even as your eyes start to glaze over with all of this complexity, it is complex and it's hard to get right and it's expensive, and you need someone 24/7 on site perhaps to actually make sure to respond to all of these things. So a lot of what you get in the so-called cloud is the virtualization of these services. You get the illusion of multiple switches, but there are actually multiple physical switches. You just don't need to know about the actual wirings thereof. But this really is a theme, right? As soon as you see a single point of failure, it's an opportunity to actually improve there. And this picture, too, doesn't need to be taken literally. We don't necessarily need to buy a new load balancer just to do database replication, database load balancing. It can be the same device, just operating on a different TCP or UDP ports. But this theme of doubling resources is actually quite common in approach. Yeah?
So the MySQL, like the MySQL database, can it store like images or other types of data?
Good question. Can a MySQL database store images and other types of binary data? Yes. You can store them in blob fields, binary large objects. Typically, this is one of these religious things. I would typically say you shouldn't store images in the database, since they're really meant to be storing data, whereas a file system has been optimized over the years for files. And so indeed what you would probably should do is store the paths of files or the file names of files in your database, but then store on disk somewhere on an actual web server or something called a CDN, Content Delivery Network, the actual files. Like Akamai is one, and Facebook has its own now. that just stores static content.
So where would that be in the picture?
So it could be so for the CDN type services. So if you were hosting it yourself, the CDN would live at the web layer, which is those 5 servers up top there. They're just web servers. But typically CDNs are so intellectually uninteresting that they're typically outsourced to people like LimeWire, one of the two. One of them is P2P, peer-to-peer, or Akamai or some other services. Amazon has their own as well.